Okay, so here is a heating curve for water. And this is expanded, and we're looking at a temperature range from minus 25 degrees Celsius up to 125 degrees Celsius. Adding heat, and here the heat added actually has numbers on it. And what we're doing here is we're looking at the amount of heat for 1 mole. This is all for 1 mole of water. So if you start with water in the solid state, frozen water at minus 25 degrees Celsius, and you add energy to it, the temperature will go up. How do we calculate the relationship between increase in temperature and amount of heat? It is in chapter 6. Q equals MCAT. Q equals MC delta T. So that's going to be used for this first transition here, where the ice is warming up. You're going to need the mass of the water. Since this is 1 mole, it would be 18 grams. You use the specific heat capacity of ice and the change in temperature. The change in temperature will be the final temperature, 0, minus the initial, negative 25, so a positive 25 degree change. You can calculate that. There's the amount of energy needed to warm up the ice. Once you get to the melting point, the ice begins to melt. So as the ice melts, we calculate that amount of heat using the heat of fusion, just like we did with the heat of vaporization. So the heat of fusion for water is 6.02 kilojoules per mole. For 1 mole of water, we're going to get 6.02 kilojoules. Then the water will begin to heat up. Anytime the temperature of something is changing, you're going to use Q equals MC delta T to calculate that. So the mass of the water times the specific heat capacity of liquid water now, times the change in temperature. The change in temperature is the final temperature, 100, minus the initial temperature, which is 0. So that'll end up being 7.52 kilojoules for 1 mole of water. Once we get to 100 degrees Celsius, the water begins to boil, and it will continue to boil at 100 degrees until it is all converted into the gas state. So we calculate the amount of energy needed here using the heat of vaporization, 40.7 kilojoules. After it's all turned into a gas, if you continue to heat it, the steam will increase in temperature. There's an increase in temperature again. Use Q equals MC delta T to calculate that using the specific heat capacity of steam. And so going up 25 degrees would be 0.904 kilojoules. So you will be asked to calculate amount of energy needed to take something from one temperature to another through state changes. And the way you approach this is you draw a heating curve like this. It does not have to be beautiful. But heating curves have straight lines. They're not curves, they're straight lines, even though they're called heating curves, right? Each state heating, the temperature going up would be a straight line with a positive slope. Anytime you have a phase change, melting or boiling, you're going to have a flat line, a horizontal line. To find the amount of energy, you look at where you're starting and where you're ending up, and you're going to have a separate calculation for each straight line. For the sloped lines, you use Q equals MC delta T. For the horizontal lines, you use either heat of fusion or heat of vaporization. And then you add them together. So, let's do an example here. Calculate the amount of heat needed to take 1 mole of ice at minus 25 degrees Celsius to steam at 125 degrees Celsius. So this is exactly what was described in the heating curve on the previous slide. So I'm just going to draw a very rough heating curve here. Well, it's supposed to be a horizontal line, but you get the idea. So the question is telling me that we're starting at minus 25. So my starting point here, I'm going to label minus 25 degrees Celsius. And the final temperature where I'm ending is plus 125 degrees Celsius. So at minus 25, the water is frozen. At 125, it's in the gas state. So I've got the ice heating, melting, the water heating, boiling, and then the steam heating up. You just have to think through what does it do? Well, at what temperature does the ice melt? At 0, right? So that's 0. And at what temperature does the water boil? At 100. You should know those numbers. So I'm going to have 1, 2, 3, 4, 5 calculations. It just gets a little tedious. So I'm going to label these 1, 2, 3, 4, and 5. Separate calculation for each line segment. Okay, so for number 1, I have ice changing temperature. So I'm going to use Q equals MC delta T. Anytime the temperature is changing, that's what you're going to use. If you try to use that on a horizontal line, you'll see that the change in temperature is 0, and so it's going to go to 0, and that should alert you that maybe don't use that one. Well, what's the mass of ice that I have? I have 1 mole, right? What's the mass of 1 mole of water? 18.02 grams. Just use the molar mass and convert that to grams. Then I need to multiply by the specific heat. This is ice, so I want to use a specific heat capacity for ice, which is 2.09. 2.09 joules per gram degrees Celsius. And then the temperature change, the final temperature minus the initial. This is not the whole range, minus 125 minus 25. It's just for this line segment. So this line segment goes from negative 25 up to 0. So here I've got 0 degrees Celsius minus negative 25 degrees Celsius. So then I can calculate that. 18.02 times 2.09 times 25. So that's going to equal 941.54 joules. The grams cancel and the degrees Celsius cancel. It's important to write the unit because some of these will end up kilojoules and some will end up joules, and that'll mess you up if you're adding later. So any questions about that one? Yes, it would be 3 sig figs because of this one. The temperatures, they're a little sloppy with the sig figs. 100 and 0 could be considered exact. Okay, so for the second line, that's the ice melting. So there's not really an equation for this. The amount of heat is, we're going to use the heat of fusion. So we're going to we have 1 mole of water, and we're going to multiply by the heat of fusion. So that's 1 mole times 6.02 kilojoules per mole. So that ends up being 6.02 kilojoules. For line 3, we have temperature changing again. So here we've got Q equals mc delta T. Well, it's the same 1 mole of water, which weighs 18.02 grams. But now it's a liquid, so I want to use the specific heat capacity of water, which is different. 4.18 joules per gram degree Celsius. And then what's the temperature change for line 3? It's going from 0 to 100. So it's 100, the final temperature, minus the initial temperature. So I'm getting 7532. .3 kilojoules. Yes, it's joules. Thank you. Joules. This one's kilojoules. This one's joules. Line segment 4. Well, we've got water boiling. So we're going to have the amount of water, 1 mole, times the heat of vaporization. So 1 mole times 40.7 kilojoules per mole. That's going to be 40.7 kilojoules. And then there's one more, the steam heating up. And so there we've got Q equals mc delta T. (18.02 grams). Now we're using the heat capacity for steam, 2.01 joules per gram degree Celsius. And the temperature change for this line, it starts at 100 and goes to 125. So final minus initial, 125 minus 100. So 18.02 times 2.01 times 25, 905.5 kilojoules. Yes, thank you. Joules. I was just seeing if you're awake. None of the individual steps here are difficult. We've done these before. What's challenging for a lot of students is putting them together. And so being able to write stuff down is a great thing. Okay, now we have to add these. So I have things that are joules, and I have things that are kilojoules. So we need the unit to be the same so that we can add them together. Just kind of looking ahead, you can tell that this is probably going to be, kilojoules would be a good unit because we're already at 40 here, kilojoules. And so this might be a really big number to be in joules. So let's convert all of these to kilojoules and then do the adding. So let's just look at this first one. So 941.54 joules. And if I want to convert this to kilojoules, I'm going to put my units in like that, and then I'm going to ask myself, well, what does kilo mean? Kilo means 10 to the 3. I've got kilo on top, I'm going to put 10 to the 3 on the bottom. And so when I do the math, I get 0.94154 kilojoules. Now, you don't have to write all of that out for the others. You can look at that and say, oh, I knew it was moving the decimal 3 places, but I couldn't remember which direction. This shows me I need to move it to the left. Okay, so this one then is 0.94154 0.154 kilojoules. This guy, moving the decimal point 3 to the left, is going to be 7.5323 kilojoules. That one's already in kilojoules, and this one is going to be 0.90550 kilojoules. And you add those up. We got 56. Anybody else get that? So adding all of those up, don't have much room left here. I'm getting 56.09934. So for significant figures, you would look at the decimal place for all of these guys. It should be here and here. And we're going to see that this 40.7 is actually has the fewest number of decimal places with just 1. So we're going to round this to 1 decimal place. So that's going to round up to 1, and so it's going to be 56.1 kilojoules. Any questions? There's lots of different problems that can be done. If it's not water, you're going to have to look up what the melting point and freezing point are. You could start here and end up there. I mean, there's all different sorts of things. So draw a picture and figure out what lines you need to calculate.